Thanks for coming. Yeah, so as Tony said, this is the third talk in the three-part series that is joint with Lijie Chen from MIT, the previous one. And indeed, we're not going to rely on the technical contents of the two previous talks. I'm going to just remind of the technical stuff that we actually need to know in the upcoming 5 or 10 minutes. And the three-part series was intended to survey some of the recent developments in randomization. And today I'm going to talk about a recent work from last year that is joint with Lijie that I'm super excited about. Yeah, let's do a recap. This is what we actually need to know in terms of technical contents, and this is going back to the late 90s or early 2000s. So in our minds, what we have is PRGs. The PRG takes a short random seed and stretches it to a long string. That string is pseudo-random. It looks random to all efficient distributions. And in the context of the randomization, what we actually care about is the output set of the PRG. Because we are going to enumerate over all the seeds. So we're actually thinking of the PRG as something that enumerates over all the seeds and outputs the pseudo-random set. And the pseudo-random set is our object of interest. And furthermore, we care about a specific type of PRGs. These are usually called reconstructive PRGs, and they work like this. They think of it as input. This is not the short random seed. This is sort of like an input oracle to the PRG, a hard string, which I denote by F. And I denoted its length by big T. And they map this hard string to the pseudo-random set. So G here is G with oracle access to F, and S1 up to S poly T are the seeds when we enumerate over them. And for this seed, we output a string of length slightly smaller than T. So we effectively mapped this T-bit string to poly T strings, each of length slightly smaller than T. And this thing should be pseudo-random. Why is it pseudo-random? Well, we have what we call reconstruction arguments. We're saying that if there is a distinguisher for the pseudo-random set, then we can transform it to something that computes the hard function, which is a contradiction because the function is hard. It cannot be computed efficiently. Thus, there is no distinguisher for the pseudo-random set. And in the first talk, we started to see a reconstruction argument. We didn't finish the entire proof, and I'm just going to come to the bottom line with one flavor of a reconstruction argument. And this is something that we'll need today later on. So I'm using this ad hoc definition of a learning algorithm. The usual definitions are slightly more general, but this is good enough for us. So a learning algorithm takes as input query access to a function. We think of this function as the function such that this is its truth table. Right? So it's a T-bit function where T is like log of big T. And it doesn't know the function, it doesn't have a description of the function, no one tells it in advance what the function is, it just gets query access to this function as a black box. It's probabilistic, it runs, and with high probability, it outputs a circuit that computes this function with less than 1% of errors. And of course, we can do this with 2 to the T queries, right? Just query everything and output the circuit with 2, but we want something much more efficient. Running time, I don't know, 2 to the little o of T, or something like that. And for random functions, of course, we cannot learn random functions. They don't have small circuits, let alone we cannot produce these small circuits by just making a few queries. So we expect to be able to learn only simple functions. In some sense. Functions such that we can look at a few random places and have a circuit that computes the entire string with a few errors. Questions about this? No? Okay, good. So this is a reconstruction argument. It follows from Nissan Wigderson and 2 works by Pagliazzo and Wigderson. It says the following. If there is a distinguisher D for this PRG over here, the PRG that takes F and maps it to the pseudo-random set in a way that I haven't mentioned, but it's not crucial. So if there is a distinguisher D, then there is a learning algorithm for this function F. And that learning algorithm runs in time 2 to the delta T, where delta is a small constant. It could be as small as we want. We will paint the parameters of the PRG. So it's a very efficient learning algorithm. It runs in time much, much smaller than 2 to the T. And the notation here is a bit dense. So what's going on? There is this algorithm learn here, that gets query access to the function f, and ignore this part for a second. And it outputs a circuit C sub f that computes f. And of course, everybody wants to use the distinguisher because the hypothesis is that we have a distinguisher, want to use it for learning. So both the learning algorithm and the circuit that it produces use the distinguisher. So the reconstruction that is asserted here says that if there is a distinguisher for the PRG, we can learn the hard function. We can efficiently produce circuits for it with a few queries. And as a corollary, these are the results from the late 90s and early 2000s. These are the classical results. Well, the top one says, it's right over here, so we see the reconstruction statement. If there does not exist a small circuit that computes f with less than 1% errors, then G with f is a PRG. Because if such a circuit does not exist, obviously we cannot produce it by a learning algorithm. And we also have standard ways to bridge the gap between this 1% errors and like failure on some input. So we have the stronger statement that if there is no small circuit that computes f, meaning that every small circuit errs somewhere on at least one input, other than this big 1% chunk of inputs, then G with some error correcting code applied to f is a PRG. So we use the error correcting code to bridge the gap between this 1% errors and the guarantee that there would be at least one error. And this is the equivalence that we saw. This is a classical result for all we are concerned right now. PRGs for circuits exist. And by circuits, I mean circuits of size that is close to this size, let's say linear size. If and only if there exists a function that does not have small circuits, that is computable in time, exponential in its input length. It's 2 to the small t. Effectively meaning that we can write down this string efficiently. Questions about this? Good, because this is the entire technical content that we need to know for moving forward. For the randomization. We look at how classical algorithms work. So we fix a machine. This is some polynomial time probabilistic machine. Okay, and without loss of generality, this is a complete problem. So we know what that is, no problem. And we get an input x. And we want to simulate m on x. So far, so good. So we write down the truth table of a hard function f. Right, this will be a flank t, which is, I don't know, n to the middle. Polynomial in n. Right, let's make it less dramatic, okay? N to the 100th. There's no need for huge constants. And we just write it down. Why can we write it down? Well, we assume that there is an explicitly computable hard function, so we wrote it down. Then we transform it to a set of pseudorandom strings. This GF is 1. We evaluate M on this pseudorandom set and we take the majority. This is how the randomization algorithm works in the classical sense. And why does it work? Well, assume that there exists X such that M with input X is a distinguisher, meaning that it behaves differently on the pseudo-random set and on full random sets. In this case, the following circuit is a distinguisher. The circuit C sub X that takes an input and evaluates M with input X with this input. So if there exists an input such that M is able to distinguish, then there exists a circuit that is able to distinguish. Meaning that the learning algorithm, when given F and this distinguisher C sub X, produces a small circuit for F, which is a contradiction. This cannot be. So we just said F does not have small sockets. So far, so good? I see a bit of puzzled looks, so it's a good time for questions. Oh, good. Okay, thank you very much. There exists a person who understood. So let's look, this ends the recap. Now we're moving forward. Let's look at what's going on here. I claim that what's going on here is really non-intuitive, non-natural, puzzling, and even a bit annoying. Okay? So we want to simulate the machine M on the input X. The first thing that we do is forget all about X. We just sit at home and write down, produce from thin air a hard string F, then transform F into this pseudorandom set. After we did that, we remember that we had X in the beginning. It's like, oh, we actually had an input. So we go and evaluate M with X on this pseudorandom set. This is a black box approach. Why? Because to produce a pseudorandom set, we don't even look at the input. In particular, we are going to use the same pseudorandom set for all inputs of the given length. Okay. Well, the main idea that we will see today, this underlies all the results, is very simple. And this is the most important thing to take from the talk, even if later on all the technical stuff, I won't be able to communicate well. So let's just focus on this. The main idea is to produce this F from the input. So instead of F, which is the truth table of a hard function, I now think of F of X as some string that I was able to produce from X. So we will extract from the input information F of X that we will use to de-randomize. Now, of course, we have to adjust our expectations. We can't expect this pseudorandom set to be good for all inputs. Otherwise, we're back in the classical regime. So our expectations adjusted accordingly are that the pseudorandom set that we produced from X will be good to de-randomize M with this specific X only. And this is what we call non-black box randomization.
Why don't you also give M as an input?
Well, without loss of generality, M is just a machine for a complete problem. I know what it is. Like, I'm not going to use the information in M in any meaningful way. And also, like this argument, I think is the most convincing one, the one that I just told you, but there is a more intuitive sense, like M is just one fixed machine, it's 1,000 bits. X is the input that grows, it has a lot of length. Okay, I saw you nodding, right?
Yeah.
Good, thank you very much, okay. So this is non-black box randomization. It's non-black box with respect to the input. We are going to produce pseudorandomness for that specific input. And one obvious question is, why is it even good? I mean, black box randomization seems better. We have one pseudorandom set that's good for everything. Okay? And the answer here is twofold. This is actually very, very good, not just because it's a fancy, shiny technique. First, we're going to materialize this approach with inherently weaker assumptions. We are going to avoid the paradigm of circuit lower bounds and these classical PRGs. We are going to try and find the right assumptions for the randomization. Assumptions that do not go into this regime, but that are closer to an equivalence between the randomization and hardness. This is the first advantage. The second advantage is that certain results provably cannot be achieved in a black box way. Achieving such results in a black box way is too much to hope for. We can only achieve them in a non-black box way. So the second advantage is that we can also get stronger conclusions. And today we are going to see one of each. One result that gets conclusions that are impossible to get with the black box approach, and one result that gets promise BPP equals promise P, essentially, but with much weaker hypotheses. And obviously, you look at this, what I wrote here, mapping the input to this hard string, is not a new idea. It cannot be a new idea. This is the first thing that you would try if you approach the problem. And indeed, following these results from the late 90s, as early as 2002, this is the first paper that I'm aware of, there was a long sequence of papers trying to materialize this approach in various ways. And the problem, this was initiated by Goldreich and Wigderson in 2002. At the time, it was called typically correct derandomization. And there is even an abstraction of what's going on here. The notion of producing pseudorandomness for X that is good for X, it was introduced by Goldreich in 2010. It's called targeted PRGs. The target is this X. So, of course, this has been studied. This is the most natural notion. The problem is that until last year, we didn't know how to do it well enough. So only last year, we were able to get conclusions such as worst case derandomization and to avoid hypotheses that talk about circuit lower bounds. So far, to materialize this, we needed circuit lower bounds, and we only got average case derandomization or derandomization that errors very rare. Questions about this? All right, very good. So let me mention in advance and in a hand-wavy way the results that we're going to see. We're going to see two results from this work with Lijie from last year, and both will rely on the similar form of assumption. So I'm going to write the general form over here, and then later on we will instantiate it per result. So the assumption is that there exists f from 0, 1 to the n to 0, 1, and now it might have multiple output bits, which of course makes sense if you look at what's going on over there. This is not necessarily the precise same f, but at least intuitively you can think of this f as that f, as a first order approximation before we go into more detail. And this f is computable in deterministic time, polynomial in some t, and is hard. Oh, you know what? I used t to denote the length, and I don't want. This is not the length of that thing. The length here is r of n. T is just a running time. So it's computable in some polynomial in t, and it's hard for probabilistic time t. I'm going to write here small. There are additional terms and conditions for every result, but this is the general form. So the general form is just a function with multiple output bits that separates probabilistic time from deterministic time, the most natural thing you would expect, right? Because to simulate probabilistic time and deterministic time, we separate probabilistic time from deterministic time. It's like the general conjecture of Cozen from the 70s that we should be able to do this for every pair of classes.
What's t? Like, what's the? Is it?
I don't know.
For any function, that's assumption, or?
No, we're going to instantiate it per result, but basically it will be like it doesn't even have to be O of 1. If the gap is larger, you'd get slower randomization. Just
how does it depend on R and?
so R will always be like a smallish. It would be n or n to the epsilon. It would, and this thing, think of it as a large polynomial or maybe sub-exponential. Yeah. Any other questions about this? All right.
This R is not, it's not, you know, one bit, it's the output.
What was the question? If it matters?
Yeah, as opposed to the function just being Boolean.
We only know how to get this with functions that have multiple output bits. Okay. For certain results, like it's impossible to get it with one output bit. I'm going to show, like in the next half of the talk, this will be very clear. There are certain notions of hardness that we will need that do only exist for functions with multiple output bits. Okay, so the first result, which we'll see in the first part, is a free lunch derandomization. This is not a formal statement. This is just me waving my hands a bit. So if you recall, in the first talk among the three, we saw something like this. Probabilistic time C can be simulated deterministically. So this is probabilistic, this is deterministic. We de-randomize in time n times t. So this is under very strong circuit lower bounds. And this is the randomization with very little overhead. We just pay a multiplicative overhead in terms of the input length. This is good. And I also said that under complexity theoretic assumptions, under sharp NSETH, which you can ask me about later, this is optimal. You can't do better. And I mentioned that today we're going to bypass this lower bound, this impossibility, and we are going to see something like this. Probabilistic time T is contained on average with respect to a notion of average case that is very strong and that I'll talk about in deterministic time n to the epsilon times t, where epsilon can be as small as you want. This thing can only be achieved via non-black-box randomization. So we are going to see the randomization that if you are willing to allow a negligible fraction of errors, you get this randomization essentially for free without paying in the time overhead. And the second result that we are going to see refers to the right hypothesis. For the randomization. And to explain what I mean, we may recall the big table that we had in the first lecture. So I just mentioned that, okay, if we have lower bounds for circuits, and being informal, of course, then we have a PRG for circuits. We just saw this. And this gives us the randomization in a black box way. And if you recall, we also mentioned in the first talk that if we have lower bounds for algorithms, not circuits, but just Turing machines, then we have a PRG for algorithms, which gives us the randomization on average. And here I'm lying a bit because we don't even know that very well. We have some scaling issues. We need to adjust all these statements just a little bit, but morally, we know this. We know this for most parameter regimes. More or less, morally, this is true. And the thing is, what's really missing here is the middle row, where we just want BPP equals P. We don't care about getting it in a black box way using PRGs. Forget about PRGs, forget about black box randomization. We just want sufficient and necessary hypothesis for the randomization. And we're going to see this result using, of course, a non-black box technique. And it will be lower bounds for algorithms with a special notion of hardness. I'm going to call it on almost all inputs. We will see this in the second part of the talk. And my plan right now is to state and prove this first thing during the first half, and then to state and prove this thing in the second half. So if there are high-level questions or things that you're interested in, now would be the great time. Things are clear? Any questions?
Sorry. I was gonna ask the question. No, it's just the lower bounds for algorithms. Is that of this type? What kind of low?
where it will be a lower bound of this type, where the notion of hardness will be a very strong notion of hardness. It won't be just, oh, every algorithm fails on an input. It will be this notion of hardness that I call almost all inputs, and we're going to go into in depth, and it will require multiple output bits.
You don't know any connections between that kind of a lower bound algorithms and regular lower, the other more standard types of,
This is stronger than the standard type.
but it's multi-output.
Yeah, well, at least, yeah, if I use an indexing function, I can get that somewhere I fail, right? If I extend the output by I, and then I have to output the ith output bit, then I get the standard notion where for some I fail.
But then it's I don't know if that's, anyways, it's non-explicit then, so wouldn't that be non-constructive?
No, it will be constructive. Like I'm saying, if I have a function, well, we haven't seen the notion yet, so maybe when we'll see it, but it's stronger.
Okay.
Good. If things are clear, let's do a free lunch randomization. It's an easier proof that showcases the main idea. So I need to introduce one notion in order to say what the exact hypothesis is. So first, a definition. I'm going to say that an algorithm A on input X approximately prints a string f of X. If A on input X prints a string that has only small corruption with respect to A, f of X agrees with f of X on almost all coordinates. So if indices such that A of X index I equals f of X sub I, and most, say 99%. And we recall now a standard notion, the standard notion of a direct product. So I'm taking a function f of z, and I'm defining the k-wise direct product, f times k. This is times, this is small, and this is k. It takes its inputs z1 up to zk, which we think of as independent, right? And it simply evaluates f on each of them and outputs the k bit string. F of z. And we use this to make functions harder. So if every algorithm that runs in time t fails on 1% of the inputs here or more, we know, and this is true for any function, this is true unconditionally, this is simply a result. I'm hand waving some technical details, but it's still true, that every algorithm that runs in time approximately t here fails to approximately print the k-wise direct product on more than 99% of the inputs. And at least intuitively in high level, this is what you'd expect to happen. But imagine that there is this hard core of 1% inputs on which you fail. And I would choose k instances uniformly at random and take k to be large enough. Well, you expect to hit this hard 1% a lot of times. So let's say we hit it here, here, and here. And whenever we hit it, we are unable to compute the function. So we are at most able to compute this string with high corruption. And indeed, the proof is a bit more subtle, but this is the high-level idea of the proof. And again, this is simply true. If I replace time by non-uniformity, by size, this is true for any function, and it's even true for time with some caveats. Okay. So a common conjecture is that for some functions, the k-wise direct product is hard even for larger time, not only for a higher percentage of inputs. And this is also intuitive, because think, for example, of f whose complexity is t. Exactly, this is a matching upper and lower bound. it takes time t to compute f. So an extreme version of the conjecture would say that if I take k independent inputs, I would need to spend time t per each of the inputs. So the time complexity of this thing would be k times t. It's essentially, this version is called the strong direct product hypothesis. And it essentially says that for these types of functions, you cannot batch compute. I give you k instances, you have to spend time t per instance. We don't expect this to be true for general functions. It's known to be false in some settings, but it makes a lot of sense that some functions will be like that. All right. So now I'm going to write maybe I can do it over here. And I know I need to write large. So fix the value of k that will be good for us. This is an ad hoc definition. K, which is n to the epsilon. We say that the function has the alpha mildly strong direct product property if the k-wise direct product of f is hard to approximately print on more than, say, it's hard to approximately print where every algorithm, every time t times n to the alpha probabilistic algorithm fails on 99% of cases. What is the meaning of this? This is exactly like what's written over here, except that the running time now increased by this factor of n to the alpha. We think of this alpha as much smaller than epsilon. So the maximal increase that you would expect would be t times k. And we are saying that there is some increase. Think of alpha as very small. When we took a k-wise direct product, there was some increase in the hardness in terms of finite. And now I can write the theorem statement. Here. Assume that there are one-way functions and that there is an f from n bits to n to the epsilon bits, which is computable in deterministic time t prime, which I'm taking to be t times n to the epsilon, but ignore this for a second. This is parametrization. It's computable in deterministic time t prime and has the 2 alpha mildly strong direct product property for probabilistic time t prime times n to the minus alpha. I'm going to, let's parse this before we go to the conclusion, okay? It's a function in deterministic time t prime, which is hard for probabilistic time slightly smaller than t prime, but whose complexity increases above t prime when we take the k-wise direct product. So just as a drawing, So initially, the one-bit function is computable in time t prime and is hard for probabilistic time t prime divided by something small. And after we take the k-wise direct product, each bit is still computable in time t prime, right? It's a direct product. But approximately printing the string, this is each bit in time t prime. But approximately printing the entire string cannot be done in time t prime times n to the alpha.
Wait, what is the relationship between alpha and epsilon?
Alpha can be any constant, but think of it as very small. Like the smaller it is, the harder it is to prove the theorem. All right. So the hypothesis is that probabilistic time t is contained on average in deterministic time t times n to the epsilon. And the notion here of average is that every problem in probabilistic time t can be solved in deterministic time very close to t with a small percentage of errors over the uniform distribution, just over the uniform one. This small can be an arbitrarily small constant. So indeed, this is weaker than the notion of hardness that I promised you. I'm going to talk about the stronger version, I think in about 15 minutes. I want to prove this weaker version just as a warm-up to get used to the ideas. Yeah.
Do you like need this particular structure of like direct products for the derandomization, or
Yes.
does it also work if you just assume there is a function so that each bit takes
True.
like that property?
It would work. But note that the structure of direct product also guarantees you average case hardness. Every algorithm fails on 99% of the inputs. So the notion of direct product gives you all these properties in a natural and free way. Each bit is computable easily, printing the entire string is hard, and it's hard for the vast majority of inputs. Thanks, good question. All right, let's see the proof. Okay, what we get is a machine M that runs in time t. And I'm sorry, I forgot to say t is a polynomial in this result and throughout. Okay, so it works for polynomial time. We get a machine that runs in time t. And the first step, recall that we assumed one-way functions. So just as a preliminary step, using one-way functions, we can assume without loss of generality that the number of random coins of M is at most n to the gamma, where this gamma can be as small as you want. This is the only place where we use one-way functions, and they are known to imply it. We can shrink the number of random coins from t, which is what it could have been, to this n to the gamma. Now, of course, this gives us a lot just using the one-way function hypothesis, but recall that we are shooting for 0 random coins. So there is still a long, long way to go, okay? Like enumerating over this is sub-exponential time derandomization, and we want randomization with no time over it. All right, so the number of random coins is smaller. Now we get an input fixed k, sorry, k is n to the epsilon throughout. We get an input x with n bits, and we map it to the k-wise direct product. So we think of x as comprised of k chunks, and we compute f on each of these chunks. Here we get a string of length k. I want to change the dimensions a bit so this will be clear. This is n to the epsilon, this is small. Compute the k-wise direct product for k that is n to the epsilon. But it's okay because we want to produce a small number of coins. Good, we computed the k-wise direct product. Now we map this using a standard hardness versus randomness transformation. Poly K strings. There will be few strings because this thing is small, just like it happened over here. And each of these strings will be of length n to the gamma, which is the number of coins that we need. We evaluate m on the pseudo-random set and take the majority. This is the entire randomization algorithm. Get x, think of it as k chunks, compute the direct product, use this as a hard function for a pseudo-random set. Just as a sanity check, let's see that this is fast before we even see that it works. Okay? So, computing this transformation, how much time does it take? Well, we have k coordinates and k coordinates, each of them takes time t prime. This is t times n to the 2 epsilon. Again, very close to t. Computing this transformation has nothing to do with t. This is a transformation on a k-bit string. So it's time poly k, I don't even count it. It's poly n to the epsilon. And in the end, taking the majority vote, well, we have poly k strings, and each of them we run a t time computation. So again, this is t times n to the O of epsilon. This is it. This is the randomization algorithm, so of course it's very fast. Now, why does it work? This is the question that we're actually interested in. So we're going to use the property that is exactly what you said. Each bit is computable in time t prime, but we cannot approximately print the entire string in time that is slightly larger than t prime. Okay, so let's fix x. So we're fixing a particular input x. And our goal is to approximately print the k-wise direct product very quickly. It will be a contradiction. So assume that m with x is a distinguisher. Right? The randomization failed on m of x. Let's denote it by the usual thing. The effects, this is just notation. It doesn't mean anything. Okay, what are we going to do? Well, we are going to run the learning algorithm with query access to this k-wise direct product of x. So again, now this is the truth table of a hard function. With this fixed x, these are k bits that are the truth table of a hard function over log k bits. We are giving this learning algorithm the truth table and access to the distinguisher. Whenever it queries, what do we do? The sanity check that I was understood. So it's going to make a query to a bit here in this truth table.
Approximately print and then look at that bit.
So, okay, so our goal is to
our
approximate
goal.
the bit, right? But like our hypothesis is that computing a single bit here is cheaper than approximately printing the entire thing. Because computing a single bit here just means computing f on the corresponding part in x, which we can do in small time t prime.
Actually, a related question.
Yeah.
You say our goal is to approximately print the k-wise direct product. In what time? Because we can do it in time like t times 2 to the
Okay, so
n to the epsilon.
let's write the upper bound and the lower bound. So computing f can be done on a single bit, can be done in time t prime, which is t times n to the epsilon by our choice of parameters. And the hardness is t prime times n to the alpha, which is t times n to the epsilon plus alpha.
Sorry, what's gamma relative to these?
Gamma is as small as what? You're using one-way functions.
So it's smaller than all of this stuff.
Yes, much smaller than alpha.
Okay, so we're trying to get a contradiction by approximately printing the k-wise direct product in something like t times n to the epsilon plus alpha time.
Yes, precisely.
Okay.
Exactly. We're trying to approximately print the k-wise direct product. Let's write this in time t times n to the epsilon plus alpha. All right. So whenever we query, the learning algorithm queries an index I here, we simply compute f on the ith part of this. So we can answer its queries. And it produces a circuit C such that C is able to approximate the truth table of the height function when it is given the distinguisher. This is the guarantee from the learning algorithm here above. And the last thing that we do is that we run C on all of the indices I. And we print the outcome. Now, in terms of correctness, before running time, this will approximately print the KY's direct product on X. Because if M is a distinguisher, then this is a learning algorithm. We answered its queries. With high probability, it outputs a circuit that is able to approximate this string. We run this circuit on all of its inputs. We get an approximate version of the KY's direct product. What is left to see is that we are doing it in time, right? So, okay. How much time does the learning algorithm use? Well, it uses time k to the delta. Delta is that thing over here. I don't want to, like, everyone to focus too much on this parameter. It's as small as we want. So this is n to the epsilon to the something that can be as small as we want. So in particular, it's much, much smaller than this alpha that we are shooting to save. We are able to get these savings by paying in the parameters of the PRG, paying in the poly k over here, which we don't care. The bit to remember here is that the learning algorithm is super fast. It is in time much smaller than k, and in particular much smaller than n to the alpha, our savings. Each query, we can answer it in time t prime, which is t times n to the epsilon. So if you multiply these two things, n to the alpha steps, and in each step we make at most one query, we're below our target running time. Great. Now we have a circuit. The size of the circuit is at most n to the alpha, because this is the running time of the learning algorithm. And now we are going to run this circuit on all of the indices. And for each index, we are going to need to query the distinguisher, which runs in time t. So let's see, we're running this circuit on all indices, right? It's n to the alpha times n to the epsilon. And each time we are calling the original machine M that runs in time t. So it's time t. And we are again below the target running time. So there were actually two steps here that we needed to do something. The first step is this thing with the learning algorithm that is very fast and that is able to query individual bits faster than the time that it takes to compute the entire thing. The second thing is that after we did all that, we are left with a circuit, and we are using this one circuit to batch compute the entire string. So this is another saving. And I'm afraid I have no way to do it like cleaner in terms of parameters. I know that there are a lot of low-level parameters here. So I want to abstract some points to remember, if that's okay. Unless someone has questions right now. Okay, the first point, which is the most important point to take, is that we have a hardness versus randomness transformation that works instance-wise. It works for every fixed x. So for every x such that M with x is a distinguisher, we were able to quickly print the string f times k of x. In particular, since the direct product is hard on 99% of the inputs, it means that the derandomization succeeds on 99% of the inputs. For each fixed x such that we have hardness, the derandomization works for that particular x. I see some puzzled faces, so I am going to pause for a second.
The only thing that I'm confused about is this assumption about the one-way functions implying the lines as well. And where that came in, I lost track of that.
Oh, okay, so we went over this 2 weeks ago, but it requires an argument.
No, I don't mean the proof of it. I mean,
Oh.
why you need that. in this-
Oh, okay, because the hardness to the classical one takes a string and outputs strings of smaller length, right? And here we need everything to happen in time n to the epsilon. So the number of random coins that we output here should be very small. It's like the one-way functions allow us to shrink the entire hardness versus randomness to descend to the epsilon regime. But the only thing that is really meaningful that we pay heavily in terms of running time is like the running time of this machine and computing the bits of this thing here. But all these transformations over here are over n to the epsilon bits. Was that clear enough?
It's okay. It's not, I just having trouble keeping track of it all.
Okay, then for sure many people are having trouble, so maybe I should pause.
Go over again the third bullet point. I'm a little bit lost.
This one?
Yeah.
So the learning algorithm gives us, this is the definition of a learning algorithm, it gives us a circuit such that the circuit is able to compute the hard function on 99% of the inputs.
All right, because you're using the learning algorithm is using some error correcting code.
No, error correct, no, just, this is the definition of a learning algorithm, and this is as a black box what I want you to take. If there is a distinguisher, then there is a quick learning algorithm.
Oh, okay. So it's a result. It's not, you didn't explain it.
No.
You're using, okay.
Yeah, I'm appealing as a black box result to all the classical stuff.
Okay.
Two quick points of clarification, just so I know what's going on.
Yeah.
First, when you're querying I, each of the queries takes time t prime, but there can be at most n to the alpha. Right. So really it's like t times n to the epsilon times n to the alpha as usual, right? For all the queries together.
Exactly.
Okay, cool.
Precisely.
And then the other thing is, why is it k to the delta? I understand that the learning algorithm runs in time t to the delta, but where does k?
So the learning algorithm runs in time that is like a delta power of the length of the truth table.
Oh, the length of the truth table.
And the length of the truth table here is k.
Okay, so that t up there is a different.
Yeah, that
Okay, great, thanks.
confusing notation on my end, right?
That's fine.
Yeah.
Can you repeat what was like the distinction between X's that this works for and X's that this doesn't work for, and why is it most of them?
Good. Okay, so take a look. First, I want to claim that this entire argument here says that for any fixed x, such that m with x is a distinguisher, we're able to quickly print the k-wise direct product on x. Take this as a black box. If m distinguishes the PRG on x, we can compute f times k on x. Okay, this is what this part of the blackboard shows. Now I'm telling you that the k-wise direct product has the property that it is hard on 99% of the x's. This is what we use direct products for, to be hard on most inputs. So in particular, it means that the derandomization works on 99% of the inputs. Because for any input such that the derandomization does not work, the k-wise direct product is easy. But there are only few such inputs. Thanks.
So
Okay.
do we really have to use the same x in both places? Or do we just want, so maybe something goes wrong if you fix x, but if you use the one x to generate the truth table and another x, say the complement of x to run m?
Well, you know, the complement of x and x is pretty much the same because you can transform one into the other, but you have to really use the same x up to some trivial modifications for the following thing. Well, when we want to answer the queries of the learning algorithm, we want to compute bits of the k-wise direct product on this x. So we have to know x. So this is the part in the argument where the reconstruction uses x. Good. it's a good sanity check always to look at the reconstruction argument and ask yourself, okay, where did it use the input? Here it uses the fact that it has the inputs in its hands.
I'd ask maybe a related question, although I guess this is what's going to come up in the next part. If instead of using the input X, there was just some fixed n-bit string, this whole process would work and it would be basically black box, right? But it's not going to be useful for the next part.
But
if I didn't feed X into any of this, but I fed you a string Y that was also n bits into this whole process. That wasn't part of the input.
If the whole process would work in computing f of x, even when I don't give you x, you need to assume that f of x for that particular x is hard for all the devices y, which is just the same as assuming circuit lower bounds. It's going back to the black box.
Yeah, okay.
What we'll see in the next half will be totally different.
Okay.
In terms of the hardness assumption. Okay, just a word before we go to recess. So what we really used here didn't have something to do with the direct product property. We used the existence of a function that, and the function is the mapping of x to this k-bit string, such that we can compute each bit slightly faster than the lower bound for printing the entire thing. And this hardness holds for the vast majority of inputs. For any such function, you get the corresponding derandomization. And in particular, if you assume that there exists such a function and that the hardness holds, for example, over all efficiently sampleable distributions, which is a natural thing to assume, then you get derandomization that is fast and that is successful over all polynomial time distributions. And this is the stronger version of the result. I'm just not writing it down since it takes a bit of time to write.
What is the, can you repeat the stronger version?
Yeah, if you assume that there is a function such that you mapping x to these k bits, such that you can compute each bit slightly faster than the lower bound for approximately printing the entire thing, and that the lower bound holds with high probability over every polynomial time sampleable distribution of x's.
Which in this case is the uniform one.
In this case, it was just the uniform one, because the direct product gives us hardness over product distributions, basically. But if we assume another function, which is not a direct product, which has hardness over a larger class of distributions, you just get, using the exact same argument, the randomization that holds over this class of distributions.
In the sense that like with 0.99 probability of
But it's not even 0.99. I mean, if the hardness is like with a negligible error, then you get a negligible error in the randomization. So the hardness translates to the randomization precisely, input-wise.
So should we think of that in a sense as saying that we still have some source of randomness? The source of randomness is that we take an input which is from some distribution or the uniform distribution, and this is basically showing that you can make the input and this representation of the input somewhat independent for the purposes of using it as the random bits of the algorithm.
I followed the first half of what you said, but not the part about somewhat independent. Could we take it offline?
Yeah, sure.
Okay.
Yeah, so what I was trying to say is that this written like this sounds to me like you are saying that basically you still get some randomness. If I would have given you, obviously, if I would have given you your input, then yeah.
So you're thinking of the input as randomness.
Yes.
And this is the classical way. This is Goldreich and Wigderson in 2002. How can we use the input as a source of randomness? But here we use the input as a source of hardness because we assume that there is a hard function on this input. The distinction might not seem very meaningful to you now. Wait for 10 minutes.
Okay.
So let's take a 5-minute break if that's okay. Thank you very much.
I see.
Well, you need to use your 5 minutes.
Sorry?
You need to use your 5 minutes to write. Can I ask you a question?
Oh, yeah, sure. Okay, I'm going to need like 1.5 minutes to it. I'm putting my last.
You might think. No, the dumb question. So like you're assuming these one-on functions exist, which is a really strong assumption.
Yeah.
So that bugs me.
It bugs me too.
So it's not like you drew it before, or is it like you're using weaker assumptions?
Oh, to get a super fast randomization, we need one-way functions even in the super low bounds. There's a specific problem.
That's been gained by.
If you restrict your attention only to super fast randomization, then we need one-way functions across the board. And in the black box approach, we need one-way functions to get something worse than this. In the non-black box approach, it still needs one-way functions, but you get in the world of super fast randomization, we need either the assumption of one-way functions or something much longer than
When you say super fast, what do you mean?
super fast is something like
Is it times
derandomization.
n to the epsilon, is that what you mean?
Yeah, but no, even to get something like this, we start needing either one-way functions or very strong functions.
So you're saying that if you could do that, it implies one-way function?
No, I'm saying that the only way that we know to
Oh,
do it
we
is.
know to do it, but that's very different. Okay,
Yeah,
okay.
do you want to say something about it?
Sometimes when you say things used to, so I get confused about whether it's, yeah, the difference between those two.
No, you're right, I just said we need a couple of things.
Is that what you're saying?
Oh, sorry, it's my bad. What I'm saying is. We're using them since we only have 2 ways to avoid, if you remember the hybrid argument,
Yeah,
and this is what we pay a lot for.
right.
We only know of 2 ways to avoid it. One way is one-way functions, which is obviously cheating.
Yeah, exactly. That's what's bugging me. Okay, so you.
And the other way is like lower bounds for non-deterministic circuits, which takes it.
And another thing that was confusing a little bit is you had a different parameter gamma for it, but you might as well just set it equal to something like,
0.01.
yeah, or something like, something is a function of epsilon. Anyway, that's minor, but.
Oh, you're saying, no.
No, I just, it never came into like gamma never came into anything.
Yeah, I could put it to be k to the 0.01.
Yes,
Yeah.
yeah, yeah, exactly.
Thank you very much.
Growing up here, you might this one.
Oh, yeah. I mean, there's bias.
Which is better if you want to.
Oh, it's just like, well, and then for just the bias of like, but also like, yeah, that one, right? Like, we side plots are like the summary. Even this, like,
You ready to go yet?
Hi, can I come back?
So should we continue?
Yeah, we're ready.
Perfect, thank you. So thanks for coming back. This is the second half of the talk, and we're going to talk about something which I call the right hypothesis for BPP equals P, which is a bit bombastic. Maybe I should put a question mark here, but I don't want to put a question mark here. Okay. So the first thing that I'm going to do is to introduce a new notion of hardness. It's a very natural notion that we needed and that we use and that we haven't found anywhere before. We're not sure why, maybe it was not useful. For sure, it's something that you can think of. It's not something weird. So remember, like the usual notion of hardness means that there is no efficient algorithm that computes the hard function correctly on all n-bit inputs. And we sometimes have stronger notions of hardness, like no efficient algorithm can compute the hard function on 1% of the n-bit inputs or even on 99% of the n-bit inputs. This notion of hardness says that no efficient algorithm can compute hard function on 100% of the n-bit.
But do you mean like it gets the wrong answer on every single one?
It gets the wrong answer on each and every input. It fails 100% of the time.
This is definitely multi-output.
That's definitely a
Right.
multi-output, and also like this is for circuits. This does not work for circuits. This is only for algorithms.
Yeah, sure.
Okay, the circuit, you can always hardwire some inputs. So a function, and I wrote 2 asterisks here, because as Tony said, we're going to need multiple outputs, at least a super constantly many, is hard for an algorithm class A on almost all inputs if every algorithm A from A fails to compute the hard function on 100% of the inputs, each and every one of them, of sufficiently large length. And why am I saying sufficiently large length? Because we can always hardwire finitely many, right? You can always hardwire the first 1,000. But this says, okay, after the first 1,000, after the finitely many, it fails. 100% of them always. It looks like a crazy strong notion. Bizarrely, it's not clear if it should exist, but it exists very easily, actually. So just by a standard hierarchy type arguments. So there exists a length preserving function that you can compute in time, say n to the k plus 2. You can make this tight if you want, I don't want. And it's hard for time n to the k on almost all inputs. Very easily, we're going to see it now in a minute. The idea is just to use each output bit to diagonalize against the corresponding machine. Here is f of x, I'm just defining it now. So it has multiple output bits, right? F of x, the first output bit, f of x, the second output bit, f of x, the nth output. And f of x is not mi(x_i). What do we mean by that? Look at the ith bit. Take the ith Turing machine, run it for n to the k steps. Look what it says on the ith bit that it prints. Negate it. And that's it. Like for every machine, when we reach a sufficiently large input length, we diagonalize against that machine on each and every input. Questions? Great. So this almost all inputs hardness is actually easy to get. I'm going to write a follow-up. It's just as easy to prove. If promise BPP equals promise P, then there exists a multi-output function. Let's say it's length preserving. Just for simplicity, we don't really need that it's length preserving in any way. That's hard for probabilistic time n to the 100 on, and I'm writing a shorthand here, AAI, almost all inputs. And this should be obvious by what we just saw, because if probabilistic time equals deterministic time, okay, hey, wait, I didn't write the upper bound. I'm saying that's obvious. That's computable in polytime, right? In deterministic polytime. So you can compute f in deterministic polytime, but it's hard for probabilistic time n to the 100 on almost all inputs.
So what's the polytime?
Larger than 100, and it depends on the BPP equals P. What's going on here? Nothing clever. Probabilistic time n to the 100 can be derandomized in deterministic time n to the million. And now just use a hierarchy. So to get the randomization, we need this type of hypothesis. We need a function computable in polytime that's hard for smaller probabilistic time on almost all inputs. And now the punchline comes when I'm going to say that it's sufficient to. See how I wrote it down. It's slightly simplified form. So here, assume that there is a function f. Again, for simplicity, it's length preserving, computable by uniform circuits. I'm going to explain this in a second. Size poly n in depth n squared. That's hard for probabilistic time n to the 100 on almost all inputs. Then promise VPP equals promise P. And this is the complement to this statement. And now I'm going to explain it slowly. And before going into technical details, I want to answer OR. You thought of the input as a source of randomness, but I want to insist on thinking of it as a source of hardness, because I'm thinking of this notion, a function that is hard for each and every input. Okay. So what does it mean to be computable by uniform circuits, let alone with the asterisks that I want to ignore for a second? Well, when I say computable by uniform circuits, I'm thinking of the following procedure. There is a machine M. Before it sees the input, it prints a circuit. Then it gets the input and just evaluates the circuit on that input. This is the notion that I'm thinking about. And when the way I just said it, it's basically equivalent to standard Turing machines. If you take a standard Turing machine, you can describe it as a machine that first prints a circuit, that is its computation, then evaluates that circuit on the input. The twist here is that I'm adding another constraint. Oh, wait, I don't need the mask. I'm adding another constraint, which is that the circuit that the machine prints is of depth n squared. So this is a form of parallel computation. It's not super parallel. It's not like AC0 or NC or something like that. It's like a medium depth circuit of fixed poly size. So the machine gets the input, prints a circuit of depth n squared and size poly n, evaluates that circuit on the input. And if there exists an almost all inputs hard function with this upper bound, then we get that promise VPP equals promise P. So the almost all inputs hardness for fixed probabilistic time is both sufficient and necessary for the randomization, but we still have a gap. The gap is that for the sufficient part, we need the hard function to be computable in parallel, in depth n squared.
Sorry, what did the uniform mean? I missed that.
The asterisk on the uniform, I'm going to need an additional condition on this uniformity that I'm trying to hide under the rug a bit. It will actually be log space uniformity, which does not mean, if you haven't heard it, it does not mean at all that the function is in log space. This is something totally different. In the world of uniform circuits, this is a relaxed condition. But since I don't want to talk about it in depth, I just said that these are uniform circuits and I wrote an asterisk. Good. So we see that there is a gap between the sufficient condition and the necessary one. We see that they're of the same form. There's a new notion of hardness that's sufficient and necessary. And I want to mention a comment that I cannot be certain of because it's not formal, but the comment is that I have no reason to believe that this condition is necessary here. It feels, and this is totally a feeling, it feels like an unnecessary auxiliary condition that we should be able to get rid of once we get better techniques. Of course, I can't back this up. If I could have backed it up, I would have written the better theorem. All right. The last comment before we move into the proof. Obviously, the specific constants 2 and 100 are arbitrary. You can replace them by whatever you want, as long as there is some gap between the two. The gap doesn't even have to be 100, it should be 10 or something like that, but I don't care. If you want to put 1,000 here and put 1,010 here, the theorem works. All right, so what do we do? This, I'm going to finally erase this part. Going to need this board a lot in the upcoming 40 minutes. Okay, we get an input. We start with a machine M, right, as usual. For simplicity, M is a linear time machine. It doesn't matter when we don't care about polynomial overlaps. We have a machine M and we have an input X. And you know, like what can you do? We have a hardness assumption. Right? We have we apply to X. What can you do? The idea here is not to use the output of f on X, but to use the computational history in the computation of f on X to produce pseudorandomness. So we compute f on X. We are going to do it with the circuit. We will look at the gate values of this circuit and use them to get pseudorandomness. Let's write it down. So of course we apply f on X, because what can you do? Now there is a circuit. It is a circuit of depth. We write it over here, n squared. And of size T, big T, which is poly n, using big T a lot. This is a big polynomial. This is a fixed polynomial n squared. And for simplicity, now this is a matrix. For simplicity, this matrix is exactly of length of width T. So we have exactly T columns in each row. And in the bottom of this matrix, on the bottom row, we have X, the input. These are the input gates to the circuit. Let's pad them with zeros, right? Because these are n bits, we need t bits, just let's put 0 over here. And in the top row, we have f of x. The circuit computes f of x, right? So by definition, in the output, we have f of x. And in the middle, we have all these gate values, which is what the circuit did when we fed it x, and it computes f of x. Very good. Okay, so let's start by doing the randomization. I want to show the main idea with the first failed attempt. The main idea is the most important one. After it will fail, I'm going to do a lot of technical work to fix it, but the technical work is not the main thing that you should probably remember here. The main thing that you should remember is the idea that I'm presenting now. So we will think of each row in this matrix as the truth table of a hard function. So now look at the top row. This is a string, it's of t bits. We're using it as the truth table of a hard function, and we're applying to that row the standard transformations that we saw. We're outputting a bunch of n-bit strings. This is the pseudo-random set that corresponds to the top row. We will do this to each and every row separately, right? And then we take the union. So we have a bunch of pseudo-random sets. We take their union and we claim that this is the final pseudo-random set that we are going to use. Now, why do we want it to work? It's not why it works, because there will be a bug in a second, but why do we want it to work? Assume that M with X is a distinguisher for each and every pseudo-random set over here on the right. We will reconstruct the entire computational history of this circuit, starting from the bottom and moving up to the top. For each layer, we will construct a small circuit that computes this layer. And the layer is of size t, which is a huge polynomial. We want to work in time n to the 10, n to the 50, much smaller than n to the 100. So fixed polynomial time. So how do we do it? Okay. Let's assume, just for simplicity, this is without loss of generality, that this circuit is comprised only of NAND gates, of fan-in 2. So each gate has a fan-in 2, it computes the NAND of the two gates below it. And really what we have here is a property that is usually called in other contexts, but it applies naturally here, downward self-reducibility. By which I mean that if you look at a gate over here in this layer, it's the NAND of this gate and of that gate in the layer below it. So in particular, if I want to know the value of this gate over here, it suffices to know the values of these two gates over here. And we cannot apply it naively to compute f, right? Because there will be an exponential blow-up. But if I just want to compute one point, I can do it very quickly with access to the layer below it. This is just a property of any circuit, by definition. So, okay, the base case, we construct a circuit C0 for the bottom row, which is of size about n. Because what's going on in the bottom row has no information contents. It's just x with a bunch of zeros. So we can just build it with our hands. We need nothing. Now we work our way up. So for I that goes from 1 up to d, we run the learning algorithm. We have a learning algorithm because we have a distinguisher. How do we answer its queries? Using the downward self-reducibility and the circuit that we already have for the layer below. So we are bootstrapping answer queries using downward self-reducibility and the circuit that we already have for the layer below. In the end, we get C sub D. Let's call it that D, okay? Just to be nice, this is the top row. And we just evaluate it to get f of x. We are happy. This is the main idea. It mimics a classical idea of Impagliazzo and Wigderson, but it mimics it in a non-black box way. Because this entire reconstruction argument that gets x and computes f of x hinges on getting x in your hands. Where? In the silly base case. The base case used the fact that the reconstruction has x. Without it, we couldn't have even started the bootstrapping. Yes?
So to get the learning algorithm, you're assuming that M is hard on each block, right?
So you caught me in one lie. There are two lies here. You caught me in the lie that I want to hide. So you're right that we took the union, and the actual assumption in the reconstruction argument is that the distinguisher works for each subset separately. Let me wave my hands and say that I will say something about it in the end. It's an amazing question. I just don't want to talk about it right now. We have a way to bypass it. Let's find the other lie. The reason that this doesn't work. I'm going to give a hint.
So like,
yeah.
Does the learning algorithm have some error?
Oh, fantastic. You caught the second lie too. got all lies. This is what you want to say?
Yeah, I was going to say, I don't think the learning algorithm knows everything, it knows a good fraction.
Exactly, but I get why people might be hesitant because it seems like such a minor issue. The learning algorithm does not give us a circuit that computes the layer perfectly. It gives us a circuit that computes the layer on 99% of the entries. And it really seems to be such a triviality because you just said we have a lot of ways to bypass it. Just encode the row by an error correcting code, right? Once we encode the row by an error correcting code, we moved from like being able to compute it on 99% to being able to compute it on 100%. No problem, we did it before. Big problem. Encode a row by an error correcting code. What did we ruin? Yeah, we ruin the downward self-reducibility. We actually need two properties simultaneously. One, which is trivial, getting from 99% to 100%. We know how to do it for decades. The other, which is trivial, to get the downward self-reducibility, any circuit has done. Getting them simultaneously is not trivial at all. It's actually a classical challenge that comes up again and again in many different settings, getting these two properties simultaneously. And here we need to get these two properties simultaneously in this circuit without really ruining everything and keeping the same complexity. I'm going to spend the rest of the talk just massaging this matrix such that it has the two properties simultaneously. We'll have technical details and arithmetizations and ideas and sum check and whatnot. We're going to have a lot of stuff, but it's not crucial because the high level idea to get here is that after I will massage this matrix so that it has these two properties simultaneously, we will just do this. And this will be the entire argument.
So where is the n squared important?
Good. Yuval, let's walk through the running time of this thing, okay? So the base case takes like, I don't know, linear time. I don't care, right? And the learning algorithm takes some fixed polynomial time. We can make it quick. So let's say that it runs in time n to the 10. Good, it runs in time n to the 10. So we're going to spend time n to the 10 on each and every layer here. And since we only have d layers, the final running time will be d times some fixed polynomial n to the 10. And this is why we were able to do all of this quickly. If the circuit would not have this fixed polynomial depth, but would have depth t, we would get no contradiction. We'd need to spend t steps, and in each of them spend fixed polynomial time. But since the circuit is of medium depth, we can do the entire reconstruction in some fixed polynomial time. That is much smaller than n to 100. Thank you for the question. In particular, I don't know of any technique that allows me to work with circuits of arbitrary depth here and get quick reconstruction. That is like the obvious question and follow-up question to this one, how to improve. Yeah.
Can you say in like one line why we will need log space uniform? And
because in the arithmetization, at some point, you need the circuit structure function to, I don't know if we need, right? Like I know that the only way that I know how to do it is with log space uniformity. And because somewhere we will arithmetize this and we rely on the circuit structure function having low degree, and I know how to get that the circuit structure function has low degree, relying on the assumption that the circuit is log space uniform. Okay, good. I think we're all set and we're diving into the technical, but whatever we will able to see, that's great. Oh, I think we have more than enough time. Good. Okay. So the technical idea now comes from the world of interactive proofs, and specifically from the doubly efficient interactive proof of Goldwasser, Kalahi, and Rothblum from 6 years ago already, but it's a relatively recent tool which partially explains why this wasn't found earlier. Like we're using relatively new tools. And okay, we're going to arithmetize this circuit in a nice way, and then make some additional modifications to it, and then we will get all the properties together. So just as a first thing, where should I write it? I think over here is okay. So we agreed that the circuit has non-gates. Okay, so let's look at the gate W, right? And I'm going to suppress X. X is now fixed. So W is really the value of gate W on input X. And let's say that it is fed by two gates, U and V, right? So the obvious arithmetization is that W is 1 minus U times V. These are all Boolean values. So now we'll do the arithmetic over a large prime field over the integers. And we think of each row as really the truth table of a hard function. So let's denote this as a function notation. So I really want alpha I, it's the function of the ith layer. It gets the name of a gate W. It computes 1 minus alpha I minus 1 of U times alpha I minus 1 of U. I'm just getting us used to the notation, that's all. Okay, and alpha I is a function from T to 0, 1. Expressed it in an arithmetic way, but it's a binary function and it takes the name of a gate here. And oh, you know what? I'm going to, okay, one last thing, I'm sorry. So it's not a function of X in any way. X is suppressed. It's a function that takes as input the name of a gate.
To fixed X.
X is fixed throughout. Okay, this is a matrix of gate values with respect to this particular X. So the function takes as input the name of a gate, and I'm going to write it in a complicated way that will be helpful for us. I'm going to write alpha, let's see. Alpha I of W is the summation over all pairs UV, this is in T squared, of this thing that I'm going to explain in a second, phi of W UV times 1 minus alpha I minus 1 U alpha I minus 1. And really, because like denoting it like this hides the point. The point is that we need to know what U and V are in order to compute this function. So to compute this function, now I'm going to have a complete description. Phi is the circuit structure function. So phi takes the name of W, U, and V and says 1 or 0 according to the question of whether or not U and V fit into W. So given U, we are summing over all pairs of gates. We're asking whether or not this is the pair of gates that fit into W, and if it is, we're outputting the right thing. And now I'm ready to arithmetize. So I'm going to erase this because we're not just outputting naively the pseudo-random sets over here. So let's fix a field, write it over here, field F. It's of size about T. This is not very important to get it right over here. The field can be a bit large. And we're basically applying the Reed-Muller code to each row. We're taking the low degree extension. We'll take something that is slightly more convenient, but think of it as the Reed-Muller code. So each row now is a function from F to the M to F. M will be a large enough constant that I will talk about in a second. And as usual, we are fixing some subset of the field, H, and it will be of size, let's say, linear, and we are identifying H to the M with T. So really, the part over here, this is like H to the M. So the left part, the part that speaks about true gate values, this is the part that corresponds to H to the M. And the right part, this is the extension part. And now I'm going to say, actually, this was just hand wavy, right? Now I'm going to say how exactly we arithmetize. Will I write it down? I will write it down over there. You know what? Why should I shouldn't write it down again? Because I already wrote it down. We simply arithmetize by adding hats everywhere. the formula for computing the low degree polynomial here is recursively defined with respect to the formulas below. And the only interesting part here is that we are arithmetizing the circuit structure function. What's going on if you look, like W only appears here. When I look at this function, this is a function of W. W does not appear here. These are constant terms from the point of view of this polynomial. It's only this part that contributes to the real complexity. And if the circuit is sufficiently uniform, log space uniform, we can make sure that this thing is of low degree. This is the part that I'm not getting into details about. There are several ways to handle this. In the original proof of Goldwasser, Lijie, and Rothblum, they actually used an auxiliary protocol to handle this. There was a subsequent simplification by Goldreich, which adds a bit in the complexity, but you don't really feel it here, and just allows you to deduce that this thing is a small formula, and this small formula has a low degree. Sorry for not getting into technical details here. If you believe me, later on we can talk about it. But right now, since we arithmetize the circuit structure function, we have that this polynomial is of low degree. Okay, fantastic. So we encoded each row by the Reed-Muller code. So of course, each row now is a code word, and if we can compute it on 99% of the inputs, we can compute it on 1%, 100%. The only problem is that we totally broke downward self-reducibility. Okay, we just encoded by the Reed-Muller code. Of course, we broke it. And it looks weird because if you look at this formula for alpha het of I, it looks really downward self-reducible-ish. Right? Because to compute alpha het of I, we just need to compute alpha het of I minus 1 at some points. So why do I claim that it is broken? What goes wrong? Well, the summation here is over a lot of pairs. If I want to compute alpha het of I, this row, using query access to the row below it, I need to sum over t squared pairs. In particular, I will need to run in time much larger than t, and everything is broken. I want to run in fixed polynomial time. So, okay, we have these rows, they're code words, they're almost downward self-reducible-ish. Now it's time to fix this thing. And let's see how we do. The idea here, and again, from the proof system of Goldwasser, Lijie, and Rothblum, in the original proof system, this was handled by adding a small sum check protocol between each two rounds. And here we are going to add between each pair of rows a bunch of polynomials that intuitively correspond to the sum check protocol and will allow us to like smooth the downward self-reducibility from one row to the other. So let's define them. I'm going to define alpha hat I0 of W. Now, you know, I should have written this here too. I want to write vectors on all of this. Because these are now not just the names of gates, right? These are vectors in F to the M. They're not necessarily in H to the M, the part that is the name of gates. Okay. I want to write it like this. It takes sigma 1 up to sigma 2m in H to the M times H to the M. I'm really thinking of this as two sets, each of M symbols in H. I'm sorry, let me write it in a clear way. It's just H2 to the M, okay? These are two M symbols in H. And recall that H to the M for us is T. So these are the names of two gates. These will be just U and V. I'm just writing them down in an arithmetic form. And in here, I'm going to write this thing. No, let me write it down for the first time in completeness, and then it will be phi hat of W, sigma 1 up to sigma m plus 1 up to sigma 2m, and then 1 minus alpha hat I minus 1, sigma 1 up to sigma m times alpha hat I minus 1, sigma m plus 1 up to sigma 2. It's really what's written over here It's the exact same thing, only I use arithmetic notation. Instead of writing U and V, I'm writing 2M symbols from H. Okay, and since I don't want to write so much, I'm just going to denote this by some sigma 1 up to sigma 2M of this thing that I just defined. This is a definition, f of W in sigma 1 up to sigma 2. F is just this thing.
Can I ask a high level question?
Yeah.
So you started off by saying that it's a notorious hard problem to do both of these things at one time.
Yeah.
And then you said you're going to use the
A recent solution.
long collide over. What exactly did they prove?
Oh, they I will need to spend a bit of time just to say the definitions, but they constructed a doubly efficient interactive proof system for log space uniform circuits of bounded.
Does not make, okay, that was too much for me.
I'm going to repeat this in the end. This is going to be approximately the last thing that I say in the lecture. So could you preserve the question to that point? I will talk about how the randomization corresponds to their proof system somewhere in the end, if that's okay.
Yeah, I guess it's just going to be hard. Yeah, go ahead.
Okay, let me say it another way. Right now, I'm using technical ideas that come from their work, but I'm not using any of their results as a black box. Just implementing technical ideas that are inspired by their work. Is that okay?
Yeah, I mean, so far it doesn't look like anything new. I mean, yeah.
Yeah.
Okay, just checking. Okay.
It will not need any fancy fancy tools other than IP equals P space, but I did hide the fact that this thing is of low degree and putting everything together. So I defined alpha hat I of 0, and it's really just alpha hat of I, right? And I'm defining alpha hat I of 1, which takes W and takes sigma 1, and that's the summation over sigma 2 up to sigma 2n. It computes the same thing, just like the first element now is fixed as part of the input, and we're not summing over it. And in general, we'll have alpha I j, which takes W and takes the first j inputs, and sums only over the rests. The rest, sigma j plus 1 up to sigma 2m, W sigma 1, it's the same thing here, 2m. And in the end, we're going to have, oh, this should be alpha. Right? In the end, we have alpha I 2m, which takes everything as part of its input and just computes without a summation, f, W. And right below it, I write alpha hat I minus 1, which is already defined. And let's see what we gained here. So we have this thing, which is just alpha hat I. We have this thing, alpha hat I minus 1. And in between, we added this bunch of polynomials. How many polynomials did we add? 2m, so constantly many. Not a big deal. We're not adding a lot of polynomials between each pair. And all the polynomials have low degree. We're just changing the number of summands. We did not affect the degree in any way. Good. And the point is that now these polynomials are downward self-reducible from one to the other. Because to compute the polynomial alpha hat I of 0, we just need to compute alpha hat I1 using all the values for this first element, which are just h values. These are n values. This is small. We can do it in fixed polynomial time. And of course, alpha hat I1 reduces to alpha hat I2 and so on and so forth, until the last thing reduces to alpha hat I minus 1 by this formula. Great. This is basically from the summative protocol from IP equals P space. So, I'm writing this as slightly more depth, with more depth. The depth here now is like 2m times n squared, which is just of n squared, right? Between each pair of rows, we added this bunch of polynomials. Now this is downward self-reducible because of the construction over there. And each row is a code word. At this point, we apply the hardness versus randomness transformation, the known one to each polynomial, get a bunch of pseudo-random sets, and take their union. This is so let's repeat the randomization algorithm. It takes X, it computes the gate values of F on X, it encodes each row via the Reed-Muller code with a particular convenient arithmetization. Between each pair of rows, it adds the sum check polynomials. Then it treats each polynomial, both sum check ones and the original ones, as the truth table of a hard function, applies the classical tools from the 90s, and takes the union. This is the randomization algorithm. The proof that it works goes by a reconstruction. For every X such that we have a distinguisher for each of the pseudo-random sets, we are able to reconstruct quickly the value f of x by reconstructing the entire computation here, all of these layers. Since f is hard on 100% of the n-bit inputs, the derandomization works on 100% of the n-bit inputs. I will have one last comment about the proof, but I'm leaving time for questions about the proof. Things that are not clear.
Can you go back to the point about why each of the rows is a hard function and not just one of them?
Ah, good. Okay. So this is the first lie, right?
Yes, because I don't like the first row.
Yeah.
Look at
Okay. Okay. So let's go into that lie. So what we're assuming is that there is a distinguisher for the union of the sets.
Yes.
And what our bootstrapping argument actually means is that there is a distinguisher for each and every subset. And really, I have no clever way to bridge this gap. So what we're doing is that we are bypassing it. We're taking an alternative route. We're only claiming that this is a hitting set rather than a pseudo-random set. And if it's a hitting set, then indeed it's a hitting set for each of the subsets. Hitting sets are useful for the randomization of algorithms with one-sided error. And there is a reduction of the randomizing algorithms with two-sided error to the randomizing algorithms with one-sided error. So we're actually first proving that RP equals P, and then using a reduction that tells us that if RP equals P, then BPP equals P. There are a couple of points here, okay? Like this reduction does not cost me any particular thing that you would notice for this result. For this result, I just deduced that PVP equals P. When we scale this up, we start paying for the reduction. So if I would have shown you a different argument and talked about like slower time bounds and weaker lower bounds, then you would have felt this reduction. The second point is that there is a fantastic underlying question that I don't know how to solve. Like I give you a bunch of candidate PRGs, one of them works, merge them. It's like a computational version of mergers from extractor theory. And like I know how to solve it in many settings, except one difficult setting, which is this one. I'll be delighted to talk about it later. It's a clean, wonderful problem, merge candidate PRGs. I guess that this answers your question. Yeah. There is another point that I want to make, and this is something that I'm telling you, I'm not going to prove. There is a completely alternative view of this entire construction. So the doubly efficient proof system of Goldwasser, Kalei, and Rothblum. It's a proof system for the class of functions computable by log space uniform circuits of bounded depth. in which the prover is efficient and the verifier runs in quasi-linear time. That's why it's doubly efficient. The verifier is super fast, the prover is efficient. All right. And we can think of this construction, the thing that's going on over here after we massage the original matrix, as each row corresponding to the prover strategy in a round of the proof system of GKR. This is actually true. What we are doing here actually is taking the prover strategies in a proof system, writing them down as functions, and using these functions as a source of randomness. So in the bottom row, it will be the last round where we look at the input. In the top row, it will be the first round where the prover tells us, oh, the value is f of x, believe me. Let's you catch me in a line. And the reconstruction works backwards. It starts by reconstructing the last round, which it knows, it's the input. And then it goes to the previous to last round and works its way back until it reconstructs the prover strategy for the first round. It's a completely equivalent view of the proof here. Okay. So just some takeaways. This is a new area of black box randomization. And it follows up on attempts that have been around for at least 2 decades, just that now we're able to materialize them using new tools in better ways. So we saw a free lunch randomization. If we agree to pay having a small number of errors, we can get the randomization that is non-black box and has almost no overriding running time. We saw a connection between BPP equals P and hardness for algorithms on almost all inputs. We saw that this is a new bidirectional connection that characterizes BPP equals P without PRGs. And I'm going to mention a couple of other things. Slower randomization versus weaker lower bounds. So if you recall in number 2 that we just saw, there was a gap between the sufficient hypothesis and the necessary one. The gap is much smaller in these settings. And randomization weak classes of algorithms. For example, of NC circuits. When we work here with weak classes of algorithms, we are also able to significantly narrow the gap between the sufficient hypothesis and the necessary one. And this is just a taste, like there are more results in the paper, and I know of at least 3 follow-up works that are in the process of publication right now. If any of you is interested in this, I will be delighted to talk about it. And thank you very much for listening.
Thank you.